Alright, so hello and welcome. Here we are, another day. We'll continue the journey here. Just give me a moment to make sure the audio is working. This is Stone Game 2, medium LeetCode here. Just give me a moment to make sure the audio is working. This is Stone Game. You can probably hear it. And pop out the chat. Very good. Deep breath. As always. Well, not always, but sometimes. Sometimes you feel like you need that. And we'll just get right to the next one. I was going to comment, I spent a lot of time the other day working on another question, and I realized I probably spent too much time on that. And I should probably just go faster. I think I just need to go faster. So I'll go faster. 11:40, Stone Game 2. Alice and Bob continue their games with piles of stones. So many stone games. So many stone games. A number of piles arranged in a row. Okay, a row. Each pile has a positive integer number of stones, piles of I. Objective of the game is to end with the most stones. Okay. Alice and Bob take turns, with Alice starting first. Initially, M is 1. On each player's turn, that player can take all the stones in the first X remaining piles, where 1 is less than or equal to X less than or equal to 2M. Then we set M equal to max MX. Okay, so there's M is a certain number of piles that the first player can take from. They can take all of them on all of those. And then M becomes increased to the maximum of itself, and X, okay, so M could be incremented at most by 2M. So it can be exponentially growing the set of stones that can be taken. The game continues until all the stones have been taken, assuming Alice and Bob play optimally, return the maximum number of stones Alice can get. All right, probably just like DP. Like almost all these questions are DP. There's 100 stones in the piles, and the numbers can be 1 to 10 to the 4th inclusive. And this is pretty high acceptance rate, not a crazy high submission rate, relatively high submission rate and acceptance rate, so this is not too crazy. I'm pretty sure this is like a DP. I could ponder it for a minute or two to see. I'm just going to close my door because I think my family might not appreciate me kind of yelling throughout the house. Oh, no, it's already closed. Okay, never mind. Yeah, so not sure exactly what this should be. So when looking for a DP solution, typically you want to go for like a top-down memoization first, and then basically reverse that and try to get the DP out of that. It's usually the easiest way to go. So this could be cubic time, and it would pass the test case. It should pass about 1 million to 2 million operations. Typically, will pass in LeetCode. Although there are like hardware optimizations you have to consider actually with LeetCode. So if you're doing things that are like a top-down memoized algorithm that's cubic time, is going to be a lot slower than a DP algorithm that's bottom-up, and it's just using strictly array accesses rather than like making a huge recursion tree, recursion stack, and also making calls to maps. Although you have these comparable asymptotic time complexities, you would not have comparable speeds. In fact, I think the array-based version can be many times, like about 1,000 times faster, like a lot faster. It really depends. Anyway, so okay. Optimally, so the maximum number of stones Alice can get. Okay. So normally I would take the difference between Alice and Bob for the winner, but actually we want to know the actual number that Alice can get. Okay. Excuse me. All right. So during optimal play, what I like to typically analyze when looking at games is like state machines, like game state to game state to game state kind of a thing, and try to make like a graph. And that's usually the easiest way to think about it. Number of piles, positive integer. Okay, so Alice starts first. She has M as 1. There aren't too many. There's only one option there, so that's the initial state. And So she could take all the stones. That player can take all the stones. Do they have to take all the stones? Can take all the stones? Can take any of the first stones? Alice takes 1 pile at the beginning. Bob takes 2. Alice takes 2 again. Alice can get 10 piles. Takes 2 piles at the beginning. The Bob can take all 3 piles. 10 since it's larger. I think they can. Okay, I think. So she has to. I think she has to take the first pile. Then Bob takes 2. Right. Now he could take 1 or 2. I think is the decision that Bob can make. 1 or 2. 1 or 2. And then Alice can then take. If he took 2, she could take up to 4. So she got 1, 2, 3, or 4. Okay. She could take 1, 2, 3, or 4. All right. The value m is going to be between 1 and 100. The number of moves is only going to be logarithmic, by the way. That's important, I think. Might be important. Oh, no, it's not necessarily logarithmic. Actually, that's not true. So m could be a parameter when you're looking at an array. The index could be another parameter. So depending on whatever index you have, so I think something important here is the sum of all the piles. Since every stone is going to be taken, we do actually only need the difference again, and just take the difference from the sum. Because, oh no, excuse me. Then you can calculate from the sum. You have x plus the difference plus x is going to be equal to the sum, which means the sum minus the difference is twice x, and then divide by 2. So just take the total minus the difference divided by 2. That gives you x. So we do actually only need to find the difference to maximize the difference in the direction of Alice. So that's 3 parameters for the DP. There's m, the index I, and the current amount that we're trying to maximize. I actually don't know if you even need that, quite frankly. Maybe you just need the third variable. Maybe it's just quadratic time. The third variable is just really whose turn it is, quite frankly. Yeah, because if it's Alice's turn, you're going to add. Bob's turn, you're going to subtract. That's actually quadratic, a number of variables. And then it's just a linear pass from 1 to m for all those choices, which is cubic. Would be cubic time. Yeah, you could do it in cubic time. I believe so. Yeah, I think it's simple way of doing it. The tricky part is adding and subtracting. And obviously just calculate the prefix sum as you go left to right. That's not a problem at all to calculate that efficiently. I think. Actually, you could even do a pre-computation of the prefix sums in order to calculate the left to right sum efficiently. That might be better. I probably want to do it that way. It's a little bit more optimized. I think it's cubic time with quadratic extra memory. Can I go backwards? Yeah, I think so. So actually, really only 2 variables, which is I and m, that I have to worry about, and then maybe a third is just a Boolean that tells me which players is going next, right? Whose position it is next. Yeah, that's still quadratic. It could still be a DP. You just go from right to left. So, I always struggle with these though, I have to say. I definitely struggle to like get it right. All right, so we'll do int dp. We're gonna say the turn is 2. 2 turns. We're gonna say const int bound is 101. I'm gonna say bound and bound. Actually, one of these should be n and one of these should be m. I think n is possibly smaller, so we'll put the smaller one here, n. Really, this could be just the maximum size of piles, but I think it's fine to just take 101. It's probably not an issue. Int I is 0, I is less than 2, increment I. Int I is 0, I is less than n, or j, excuse me, it should be j. J is less than n, increment j. And we're just gonna fill. I don't know if there's a multi-dimensional fill in C++. That'd be kind of nice. I kind of would appreciate that, I think. All right, that's all initially 0. And somehow I'm going to go backwards, in the backwards direction, I think. And I tend to like to actually add an extra value at the end here, maybe n plus 1 kind of a thing. Maybe that's what I want to do. I'm not sure exactly. But I know I'm going to go backwards, and that's probably going to be an inner loop thing. Starting from n minus 1, j is greater than or equal to 0, decrement j, and I'm going to say, depending on whose turn it is, it could be A or B. Let's do, probably want to do it this way. Actually, I think I need to do both turns beforehand. I think I have to do it this way. Yeah, because like I won't have the data I need on the right side if I don't do both turns. I think I have to do both turns. So both turns, it's going to be, depending on I or j, constant factor. It's better, probably better to do an array access here. I don't know if it's better an array access or just a calculation. I think the calculation is better. Just do a conversion of I bit shifted 1 minus 1. So if it's a 1, it'll stay at 1. If it's a 0, it'll go to negative 1, right? So there's that factor that's involved. And then, so it's plus or minus the amount. And there's a certain amount m. Let's do that. For int m is 0 to m is less than bound. So it could be all these values of m bound. It could be, so, okay. Let me do the pre-calculation for the prefix sums as well. Prefix of n, I think, is what I want. Yeah, that's fine. I could do it that way. And just say prefix of n. Yeah, prefix of n. No, prefix of n is fine. Partial sum is what I want. Write this into prefix and prefix plus n, something like this. And so piles dot begin, piles dot end, and write into prefix. And I think it's, I just have to double check this partial sum. Hey, how's it going, Melito? A long time no see. Hey, it's been a while. Hey man, how's it going? It's been quite a while. It's been, I feel like it's been years. How have you been? First, last, and operation. Do I need? I don't think I need a starting. This is what I was wondering. If I need a starting point. I think I just do first and last. Writes the sums. Okay, I think it's fine. I think it's fine. Yeah, well, I'm trying to figure out whether or not I need to initialize this. I don't think I do. PFX is probably better than prefix. Don't need all those letters. Okay, so I got a partial sum, got initialized DP, got this factor, 1, 1, -1, got this M value. I think, so what's interesting about this M value is what I want to do is I want to call at this point this particular function with a certain 3 variables. There's going to be I is the player's turn. Turn is probably better than I. Let's do turn. Keep that simple. And there's a certain value of M at that point that if I were to call M from that point, that's how many options I have to my right. So it's going to be, and this also is just, this is bounded as well. M is less than bound, and it's going to be I or J plus M is less than or equal to N, I think. Yeah. Right. In other words, you can't go off the edge. Right. That's another element of this here. Let's do M is 0, and then K is actually J, and let's do K is less than or equal to N. And I think it's K is less than N as well, and it's going to be increment M and increment K. Just keep it like this. I think this may be a little bit easier. So what I want to do is I'm going to get the prefix sum from 0 to M, which actually I don't really need the prefix array, do I? I don't really need that. That's kind of unnecessary. Yeah, it's kind of unnecessary, actually. Just say prefix is 0. And we're going to increment the prefix by K, piles of K. Rename this PS. Piles of K. A little confusing. Technically, you can go all the way. The value M. I'm trying to think how to do this. This actually may not be what I thought. So for a given value M, that's how many piles I can go to the right, right? Now there's 100 different values of M, though. Right, this is a triple loop, it's not a double loop, it's a triple loop. That's the thing. It's cubic time, not quadratic time. Right, so there should be a double for loop in here. There's 3 for loops because there's a 2 different turns, but there actually should be 3 loops. Okay, yeah. That's the part that I'm getting confused about. Yes. Interesting. So M is going to be between 1 and the bound. Realistically, right? Let's do that. That was right. That was the right idea. For each of those values of M, there's another loop inside, which is K. Yeah. Something like this. Fine, I'll be back. Have a few things to check first. Sure, okay, that's fine. That's fine. Yeah, sure. I appreciate you coming by and saying hello. M is always going to be at least 1, right? K or X is the value. It starts off at M. K is basically less than M. I, J, K, and then let's just say index. Say make the index start off at J, and the index is less than N, and the index is incremented. So a little bit confusing here what's going on. Yeah, definitely very confusing. I think I understand. So every value of M can be handled here. And M has to be at least 1, I think. It's always at least 1 anyway. Okay. So, M, so the value X could be between 1 and 2M. So I'm going to let this be K, and K could be, let's just say B, or bound, or UB, I don't know. M bit shifted by 1. K could be less than or equal to UB. Or actually just do it this way, let's keep it simple. Yes. So K is 1. Index IX starts at J plus 1, which is J plus K. And then we increment K and the index together, and IX can't go past N. Okay. I realize that's very confusing. This is like pretty confusing. Trying to follow this is like, oh boy. Of course. So actually one pile starts off at 0. Yeah, it starts off at, so you get some value K and some index J. The prefix is add that value of IX. And what's going to happen is we're going to add all of the, so first things first, we're calculating a difference here. We're going to add all of the, values left to right for each value K up to N up to M. To have some prefix that gets calculated. Now let's say we take a pile, we just take one element from the pile. Well, what we're going to do is the element from the pile that we take, we can recurse on dp of the other turn, right? So now it's the other turn of this index plus 1, right? That's how many piles will be left. We take this index, so we get index plus 1. And the amount, right, the value M is going to be the maximum of X and M, which is K and M. Okay, that's sort of the recursion, what's on the right side, what we expect to be there. What I expect to be there, and I'm trying to maximize that. So there's the best value, which could be optional. Actually, it should be optional. Yeah, this is confusing. And what I'm going to do is write dp of this current turn of the index j of this bound m, I'm going to write the best value to that. Okay, yeah, really pretty confusing. But so we'll say next value, and then we'll say best. So if not best, or and there's a few things to consider here. If not best, or best is less than next, set best equal to next. All right. Yeah, this is definitely confusing and hard to follow and hard to explain. I'm getting there though. It's a little bit involved. How are we doing? 25 minutes? It's taking me a while. I don't think this is that hard. It's just difficult, kind of challenging to code it properly. Also have to consider this factor. That's another element that's important here. Okay, deep breath. So the prefix, we have this k is 0, k is less than m bit shifted by 2, so less than or equal to 2m, right? K is actually going to be x minus 1. Increment k. Take the maximum of k plus 1. I'm wondering, actually, I think I can just leave k as 1. Actually, I think I can just make k exactly this. Exactly this value is fine. But the index starts at j, so when k is 1, we take just index j. Wait, so we could take that many piles, and the next value is going to be that prefix. So the prefix, it depends on the factor. So the factor times the prefix plus the dp. So this is either a -1 or a +1. And then we're getting the largest value that we can get on the dp if we go to the next index from ix with a modified maximum of k and m, which is whatever m is, and k could be larger than m or whatever it is. And then we update the best value with whatever the best is compared to next. All right. Interesting. So best hasn't been set, we set it, or if it has been set and it's smaller than next, we're trying to maximize next. Okay, that makes sense. So this happens for each value of m. We go through each value of k, which is really the choice of x, and we calculate what dp could be, and we update based off of j and m for that turn what the best value should be. And I think it's this simple, actually. I think it's like that straightforward. At the end of this, we would return dp. It would be so const diff best difference, the smallest difference, or no, excuse me, the largest difference for Alice, which it's going to be positive when turn is 0. No. When turn is 1, that's Alice's turn, right? So that's going to be positive. Turn 1 and m is 1 and index 0, right? That's the optimal value for Alice, the largest amount for Alice. And we're going to say, so also, this isn't always the case. So this is, if the factor is a -1, we have a best min and best max. So I think we want to optimize actually when it's the other person's turn. Depending on the turn, we actually want the other player to play optimally as well, which means the other player is trying to get the most negative value possible. Yeah. So the way that works, it's going to be, again, depending on the turn, you could just modify this and say, so it's going to be, so if not best, always, or, and this is the part that gets a little more interesting, the way it works is, okay, let me see here. This is like a little confusing. Let's do it this way. Let's put the or here and this here. Okay, there we go. So the reason I want to do it that way is I want to say if factor is 1 or not factor, and the other way around. I realize that's kind of involved. That's a little involved. So what's happening here is if best hasn't been set, then we're going to set best to next, whatever that value is. So just take the first one. If it has been set, then depending on the factor whose turn it is, right? Really it should be turn, not factor. Turn and factor, turn and not turn. So if it's turn 1, that means we're looking to maximize this amount, right? This is Alice's turn. If best is smaller than next, we want to update. If it's Bob's turn, then we want, when best is larger than next, we want to update next. We want to get the smallest value on Bob's turn. So the smallest value on Bob's turn, the largest value on Alice's turn. That's important too. I forgot about that. And this will get a difference between the optimal difference for Alice, and then we can just get the constant total is going to be accumulate over the whole array, PS begin, PS end. And I said X, we'll say it really would be Alice or Bob. Bob is going to be the total minus the difference divided by 2, right? And that's fine. Yeah, total difference minus 2 or divided by 2. So I think I said before, if there's Bob plus the difference is Alice, and Bob is the other value, right? So 2 times Bob plus the difference is equal to the total. That means that Bob is going to be the total minus the difference divided by 2. And I think that's always an integer too. And that means return Alice is Bob plus diff, right? Excuse me. Something like this. This is a bit hard to think through, quite frankly. A bit hard to code. 101 type bound. Oh, it's less than bound. Excuse me. That's a mistake. Yeah, I added 1 on the bound. Oh, it's correct. Look at that. Oh. Okay. Let's generate some test cases and then randomly generate some test cases. So it's going to be 100 numbers between 1 and 10,000. Okay. So generating test cases, I could just use this, write a quick script to do that. Let me try. Let's give me 1 moment to pull up a new shell. Okay, so there we go. Let's do awk script. Let's use begin. Let's do, I'm getting better at this. Date plus %s %n, get line seed, srand seed, and then just print rand. All right, let's just test this if this works. Okay, good. Now what I want to do is n is going to be int of 1 plus, we'll do 100 times rand, so 100 numbers, Have a for loop, have a variable x, which is going to be the output. I is 0, I is less than n, I. Let me just make sure the syntax is fine, it's correct. So now we're going to print x with some boundaries, so this one and this one. We're going to say x is, so if I is less than n minus 1, we're going to say x equals a comma, and with x, something like this, and then x is going to be x with an int 1 plus, we'll do, oh no, whoa, let's do, oh, okay, hold on, whoa, jeez, oh my goodness, my history just like starts going all over the place. What happened to my history? Where's what I was just working on? It like doesn't save it properly in the history. It's happened a few times where I don't want to show my commands just start going like backwards. Something. It's really weird. What is going on? Was I just... I don't want to lose all that. What is going on? I don't know if that's like a bug or something. That's really weird. But that's not what I wanted. What happened? What happened to my history? Yeah, that was weird. That's happened to me a few times where like my history is just not, it's just not the last thing. Whatever, like when I go up, it like, I don't know, the history gets into a weird state, or a state that I don't understand. It starts doing strange things, but I just wanted to go back to the last line. Anyway, yeah, so let's take that again. The reason why, yeah, because I accidentally press a button and then it like, yeah, my history ends up in a weird spot, a weird place. So there's n, let's do k and c. K is 100, c is 10,000. So it's relatively easy for me to just modify those variables. So n is going to be related to a k, and this one is going to be related to c. Yeah, so I don't have to like go through the whole, okay, so I did this wrong last time too. So I think it's the other way around. I think this has got to be on the left side. There we go, okay. And this is, I is got to be greater than 0? No. Or greater than -1? No. Is it just got to be greater than 0? Yeah, okay. That's a little bit strange. So it does, if I is greater than 0, then I add to the right of x a comma. Okay, how come I don't see a comma at the end of this one though? What? Shouldn't this one have a comma? Oh, and then I add the number afterwards. Ah, okay, that's how I should do it. Yeah, if I is greater than 0, then I add x with a comma, and then I add a new number. So the first one we don't add the comma. Yeah, okay, I always get that confused. It's like kind of, for whatever reason, I tend to get that confused. Anyway, so we can go to for I in sequence of 1 to 8, 1 to 8. Oh. Let's do j. J, do, done. There we go. All right, got it. And we have the constants k and c. So there we go, we got a bunch of different test cases. I could try a few of these just to make sure I have the right idea. I didn't make any mistakes. How are we doing on time? Yeah, 40 minutes. Okay, pretty reasonable. Let's do another batch. So yeah, it's quadratic, it's cubic time, but it's cubic time DP. It's relatively fast, and seems to be the right idea. It's pretty good. I mean, that's reasonable. There may be a much better way to do this, but I'm not gonna spend too much time trying to figure that one out. And the last one. And now I'll do a few with the numbers very tight, very close to each other, with K and with C being kind of small, like 10. Much tighter, kind of. Sometimes when you test things with smaller numbers, tighter numbers, numbers that are closer together to each other, you can run into some strange issues. So I think this is correct. Do it a few more times, a couple more times. I think the idea is there. The idea is relatively straightforward, relatively simple. Yeah, I'm using DP, obviously. I'm trying to think if there's anything else I might want to do. Let me do one more. I think I might want one pile also. This is a very high acceptance rate. What if it's just one pile? Just try these things. Sort of unusual cases, I guess. All right, it seems okay. I'm gonna go for it. Hey, you got there. Sweet. Pretty slow. Slow solution. Maybe you could do this in quadratic time. I don't realize it. That's like disappointing. It's really slow. Took a long time to code too. We submit it a few more times, like 5 more times. I think I'm gonna look at the solutions. Yeah, that's kind of disappointing. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Pretty good on memory, but it's slow. And one more submission. 1, 2, 3, 4, 5. Yeah, it took me a long time to program and ended up being a slow solution. It's very straightforward, but like relatively simple in terms of the idea. It's just, I don't know why is it so slow? It's a good question. Could do this too. Actually, no, that's fine. Never mind. I don't know. I don't know what to say here. Yeah, kind of just is what it is. I don't know what to say. Works. It's correct. All right, solutions. Let's go. Let's not waste too much time. Easy Python solution using DP. In all caps. Okay, let's do most votes. DP tabulation. 100% DP. Okay. Chrissy, yes. All right. Python, Java. Let's do the Java one. It's better. Yeah, I'm a little disappointed that my code was so slow. I wasn't expecting it to be that slow too. It was kind of surprising. That's okay, I guess. Java, tabulation. Didn't really explain this. ABC. Alex and Lee continue the games with piles of stone. Lee wins. Key comment. Okay, yeah, the explanation is what I want. Pre-sum, DFS, last player takes all, memo, current take, pre-sum, take max of current plus what's left from other player, max take. Oh, this is like really simple. Whoa. What? That's so annoying. LeetCode, why? It took me so long to TP this too. It's actually recursive memorizations more so than DP, but it's fine. You can bottom up DP here. This is cubic time too. This is. Yeah, I mean, that's what I did. That's what I did. That's what I did. Max of x, I plus x, m in the range 1 to, yeah, it's literally minus the min of that. A of I is the prefix. Okay, I didn't do this. This part I didn't do. This part is kind of what I did. Well, he subtracted the minimum. What is going on here? What? Okay, so I did things a little bit differently. That might be why mine's a little bit slower. There's a lot more machinery involved here. A lot more calculating. More thinking too. It's definitely more complicated than what's going on over here. But I don't understand this part. So what did he do? So this part is the same, more or less. Well, it's a little different. I mean, I switched between max and min depending on the players. Depending on the player, but actually, I'm not sure what he did here. Because he doesn't switch between the players. He just says, what does DP represent is probably the question I should ask. So this is going to be the smallest amount for Alice, right? And then A of I minus that smallest amount. I think this is the smallest amount for Bob, subtracting the smallest amount for Bob. And so you're going to return, come back to that in a moment too. If I plus 2 times m is greater than or equal to n, return Alice. What is A of I? N minus 2 minus 1 negative 1 A of I is equal to plus equals A of I plus 1. So we're modifying the range, modifying the pile vector itself, right? That's what this A is. And we're starting with n minus 2, and we're going backwards, and we're adding the right side. So we're creating the prefix sum from right to left. Okay. So that would be basically all of the piles to the right. Okay. Prefix sum right to left. All right. And then we're saying, so this is one for loop. Like this should actually be a triple, should be cubic time still, because I and M are I and M both range over from 0 to n, so it's still cubic time, but it's just much fewer operations I think that are happening. That's why it's so much faster. So he writes in, that's one optimization, I guess, is that instead it's the prefix The prefixes could be like pre-calculated. They don't have to be calculated at each point here. You can go right to left and pre-calculate the prefixes. And then from there, if the I plus 2m is greater than or equal to n, it's just write a of I there. Okay, so when dp on these two values, excuse me. That'll maximize a of I. You just take all the stones. Okay. I'm really confused by this. I don't know if this makes sense to me. This kind of doesn't make a lot of sense. It's not clear how, like there's basically some skips that you're able to do by considering like Bob and Alice as like a single entity, something like that. The DP is just one function. The way I did it was just calculating the difference between Bob and Alice, but then you have to have an extra routine at the end to extra routine at the end to calculate Alice from Bob, or calculate Bob and then calculates Alice from Bob from the differences. But I'm just glad I got it right. I'm just glad I got it at all. What is going on here? How did they do this? I plus 2 times m is greater than or equal to n, return a of I. Okay, that's fine. Well, that just means that you don't even need to calculate the intermediary steps. You could just take everything in one shot, right? Otherwise, there's a for loop here where you loop over all the possibilities of x and you calculate dp of I plus x and max of m and x, right, recursively. And then take the minimum of all those results and subtract that from a of I, and that's what you're going to return for that dp of im. So my question is, it's basically the sum of all the stones, a of I, at that point, minus the minimum. Oh, that actually makes a lot of sense. Oh, I get it now. Okay, that makes sense. All right, you ready? So, right, a of I is you basically want to take all the stones from left to right, and you have to subtract the stones that the other player takes, right? And you want to minimize. You want to pick x such that the stones the other player takes is minimized. Oh, I see. It doesn't quite work the same way if you DP this bottom up, because you don't necessarily know which player finishes the game. Basically, both players are considered to be the same player. Like, when you DP from Alice's perspective or from Bob's perspective, both of them basically could be considered the same player trying to optimize. Okay, that gets really confusing, but I understand. So basically, the optimal, excuse me, in both cases when they're playing optimally, they're both trying to get the maximum number of stones. So you can consider the DP to be, for either player, it's going to be the maximum amount of stones they can get. Right, okay, that's a very, very interesting kind of solution, way to think about it. That's kind of hard. That's hard to see. That's like pretty hard to think of things through straight through. It actually doesn't matter which player is being considered under the DP. Like, it's just a player at this point. There's a maximum number of stones they can get based off of whatever the other players could get. Okay, that's really interesting. That's really interesting, and I'm not sure exactly how I can bottom up this. I'm sure there's a way to do it, but yeah, it's still cubic time, but it's just a lot simpler logic. And you can just prefix it back to right. Okay, that's pretty interesting. Let me try that. Try that one again. So we're gonna DP bottom up, and this time not gonna use. And I also don't think I need I to be. I think I just can be n, by the way. Okay, let's try this. So DP prefix. Actually, we're gonna write it into this. Just write it directly. We're gonna destroy the values in here. I equals n minus 1, or minus 2, greater than 0. I, ps of I is going to be plus equal to ps of I plus 1. So, yeah. And then we can say, now bottom up, going backwards, int I is n minus 1, I is greater than 0, decrement I. Eventually we want to return dp of 0, 1. Bound is the same. And then I want to say n minus 1, 0, how does this work? So I should probably fill this DP also. Let's demonstrate that I understand what's going on here. I think I get it. I think I get it. It's a little bit, wasn't totally following what was being suggested. Trying to follow it. Don't think I totally got it, but so the idea would be, again, just the DP is just going to assume for any player, right? Try to get the maximum score. Doesn't matter which player. So what I want is going backwards from. So again, it's a triple for loop, right? Triple for loop. It's going to be for each I, but also for each m, from 1 to m is less than or equal to, I think, less than bound. And there's going to be from I, so this x, we could do x, but probably not x. Let's do k. I like k. K from 1 to k is less than or equal to 2m. And then I said there's another value, we'll call it j. J is going to be, or index, I prefer index, which is going to be I plus k, or 1. And we're going to increment index and increment k. Okay. And also this has to be, so here, so this is an optimization. If I plus m is greater than or equal to n, then we can set dp of that spot and continue. The dp of I and m is just directly going to be ps of I. Okay, now this is the prefix sums. After destroying the original values, we just get the prefix sum directly. So that's one optimization that's important, is that basically if you go all the way off the side, then that player should just take all the stones, right? And to say this is greater than or equal to n, it's basically index. So one stone, if x is 1, we take the one stone there, right? I. If there are, let's say, 3 stones, we go to I plus 1, I plus 2. So the maximum number of stones is m times 2. The index we can go to is going to be m times 2 minus 1, if that's greater than or equal to n minus 1. So this is a little confusing how we get here, but I think it's one way to arrive there, is to say if I plus 2m gets me to n minus 1, right? So I plus 1 would just put me at I is 0. So it's, or x, it's I plus x minus 1. I'm trying to think, like basically, how do I specify that, like I was able to get all the way to the end, right? Like how can I express that? The way you can express that is, where do you end up with x stones? Well, it's going to be I plus x minus 1 is the right side. So you have I to I plus x minus 1, right? Because I plus x minus 1 minus I plus 1 is x, is the size of that interval, right? If it target is t minus I plus 1, right? You want t minus I plus 1 to be equal to n minus 1. Or excuse me, you want t to be n minus 1, and x is going to be t minus I plus 1 equals x. Which means, right, greater than or equal to n minus 1. You're able to get that, at least that far. That means that, what is the value t? Well, t is n minus 1 minus I plus 1. That's so confusing. Trying to make sense of this. It's funny because like I see boundary stuff all the time, and I always just get so confused when I see it. Boundary related optimizations, like I always get so confused. Where do I end up on the right side when I add x to I? Which index do I end up at? It's x minus 1, right? Because it would be, the endpoint, we'll call it t. T is t minus I plus 1 is equal to x. What does that make? Yeah, that's actually exactly it. T minus I plus 1 equals x. So what does that make t in terms of x? That means that t is equal to x plus I minus 1, which is this one. And then so if that endpoint is greater than or equal to n minus 1, t minus x, which the largest value of x is 2m, so it'll be I plus 2m minus 1 is greater than or equal to n minus 1, which is the same thing as I plus. Okay. Yeah, it's not the most obvious thing. That's like you're dealing with like a bunch of different relationships there, but it's shouldn't be that hard to see it, but it's there. Yeah, so that's a big optimization there. If you're just right at the end, then you just DP, just take all the stones, and that's it. Your DP is very straightforward there. Otherwise, you're going to take the minimum. So optional int minval or mval, minval, and we're going to say this is going to be the smallest of its DP. So constant val equals DP of something or other. We'll come back to that. What that is. If not minval or minval is larger than val, then we're going to update minval to val. Okay. And then we're going to write in here that min value. Okay. This is going to be I and M, right? Very straightforward. And this value is going to be, this also is index has to be less than n. Just this minimum value, it's going to be dp of I plus k, which is just ix, and m, which is k, right? No, it's maximum. Excuse me, maximum of k and m. Yes, maximum of x and m, right? So that's the value that we calculate, and we're going to subtract that min value from ps of I. So we're going to take all the stones to the right, and then just minimize the next player's score, right? That's how we ATP. Yeah. That's a much more concise way of doing this. I think a much cleaner, faster, more concise way of doing it. Hopefully I didn't make a mistake. Yeah, I got it. All right, there we go. Let's print more of the, it's been like an hour in this now. It's a pretty good amount of time. Let me get more test cases here, just to make sure this is reasonable. Or if this is probably correct. Oops. Okay, let's do it like 3 times. Oh, run to, ooh, uh-oh. Oh, uh-oh, that's a close one. Good thing that's why you test things. That's why you gotta test things, man. That's why you gotta test things. Yep, very important. Just very simple, what they call a smoke screen test, where it's just like a very, it's not much of a test, but just something to make sure there weren't some small errors that were made. So this looks like it's a lot faster than what I had before. So I don't know why that one was 7, the other one was 4, I don't know. Okay, I'm gonna modify K and C. Let's make C 10,000. Let's do this 3 times. I think I got it. I mean, I basically just took another solution and then modified it to make it bottom up. But I should have been able to see that, I think. I don't know, it's kind of hard to see such things, you know, it's like you can, but it's pretty hard to see that. Excuse me, it's not that easy to see sometimes. Yeah, it could have been either player from either direction, would still work. Yeah, I don't know, it's really, I still feel like I'm kind of, I believe it, but also still definitely like not the most obvious thing. All right, let's go for it. So that's pretty fast. Definitely a lot faster than what I had before. Okay, there we go. Now we're getting somewhere. That is way faster. That's so much faster. Why is it so much faster? Oh man, come on. That's like 100 times faster. Whoa. Well, you know what I think it is because it's cubic time. The speed up that you get from doing less operations is just really dramatic. It's like cubed. I think that's the issue. Submit it 5 times. Yeah, this is definitely a lot faster. It's not 100%, but it's fast. It's quite good. A lot less memory too. Yeah, not getting 100% though. Not getting 100%. Kind of tough. I don't know what to say. But yeah, I understood the other solution though, at least. 1, 2, 3, 4. We'll do one more. 1, 2, 3, 4, 5. Okay, I feel a little better about this. Still not as fast as it could be. You know, I don't know. Gee. M probably should be bounded by n as well. by the way. Maybe that's why. Maybe that's an issue. Does it still work? I don't know. Ooh. Maybe I need that. Okay. Let's try to submit that one too. Pretty sure that's still correct. Yeah, it doesn't really change it much. It doesn't do too much if I do it that way. I mean, I could keep trying. I don't know. This is kind of. I'm wondering if it's faster if I do some of these things like constant bound or up dbound db. Some of these calculations could be removed altogether. Just try to speed it up a little bit more. Maybe. I'm trying to think here. I don't know if I use it using a Sentinel. Could try this too. Let me some slight adjustments to see if I can get this to be a little bit faster. Maybe? I don't know. Okay, it's a little bit faster with that. That's kind of good. Not using an optional. Oh man, whoa. Okay, that's getting closer. What if I'll keep that in mind. Okay, don't use the optionals. It also could be just like PS of I, or PS of 0, I think, or no, PS of 0, I think is the largest sum. Which would be also larger than anything else, I think. Technically, that still works. Could try that one. Afraid I probably shouldn't have submitted that one. Oh yeah, okay, there we go. It's a lot faster like that. Oh, almost 100%. All right, getting close. Getting close. What if I remove this altogether and I just say this is I plus k? Right, remove ix altogether. Maybe that makes it faster, I don't know. I wonder. Okay, that's pretty fast. Okay, this is a lot faster than what I had, I think. I went from like 20 milliseconds to like 3 milliseconds. This is what I was saying, is that it's cubic time. The things that I do in the code basically has a cubic effect because it's cubic time algorithm. Yeah, I think it's a little faster to just use one variable there. I'm not sure if I can do this differently. K has to be less than this, and this also has to be. I can maybe remove this one upper bound 1, upper bound 2. Maybe I could do it that way. Remove one more operation. One, two, three, four, five. Oh. Oh no. No. Never mind. Can't do that. Yeah, because that's varying as you go. Okay. Yeah, it varies as you go, the K. So I didn't really think about it. Yeah, I. Oh no, I doesn't change though. I doesn't change. I had the right idea. N minus I is the one. Ah, there we go. Okay, that's what I wanted. Excuse me. I was gonna say it was like, I think that saves one more operation. Okay. I don't know if that's better though. Sometimes a variable lookup is like not better. Sometimes it is, sometimes it isn't. 1, 2, 3, 4, 5. Okay, I'm really close. 1, 2, 3, 4, 5. Trying to get there. All right, I could probably stop here, I think. That's pretty good. It's 3, 3, 7, 3. I don't know if actually this is better to have this variable here. I wonder. I don't actually know. No, not getting 100%, but really close. Really close. I don't think I'm gonna get 100%. It's just a little too tight. Yeah. Something slight here, I'm sure. Something's minimal. Some small thing could be changed. Maybe it's this. Can I remove this? I wonder if I can remove this. Let's see. I've been wondering about this. I've been wondering about this, if I even need that. Maybe that's it. I don't know. I mean, that shouldn't change much. It also seems like it probably isn't. Maybe I should do like something like this. Oh, does this work? Might crash. Hopefully it doesn't crash. Hasn't crashed in a bit, which is good. Yeah, let me try one more time. I don't know if that matters, the initialization code. It's usually good to keep it in there. It doesn't really affect the code much, quite frankly. It doesn't take very much time to run that routine. Yeah, I don't think it really matters that much. I don't think it's going to be the difference between 100% or not. Oh, we had that back. Yeah, I don't know what to say. Sometimes we get there, sometimes we don't. 100%, or not 100%, 99%. I can't seem to get below the 3 millisecond mark though. So, all right, that's probably enough. There might be some other optimization that could be put in here. Oh, there we go. The compiler probably optimizes this out, but that's actually another one. I didn't see that. Probably is handled by that anyway. Yeah, I think that gets removed anyway. It doesn't really matter. Max of K and M. Is there a way to remove this function too? You know what I could do? I could do the following. Ready for this? At some point, this is just going to be k, or m, and at some point it's going to be k. And I could split this loop over when that occurs. So k is m, right? K is less than m, and k is less than this point. Then the max of k and m is just m. And then k is equal to m, and it's always going to be k from this point on. How about that? That's clever. Do a little bit of loop unrolling there. Okay. Does that work all the time? I'm afraid to submit this. I'm afraid to submit this. I don't know, man. Let's do one more. Or a couple more of these. Let's do this one. Some loop unrolling. Let's see how that goes. Optimization off of that. It's not really unrolling, it's just like breaking a loop into pieces. Oh, okay, that's a little better. That might be an improvement. It's getting closer. It's a new number, 4. I haven't seen 4 yet. If that's like a high roll, then the low roll might be 0. 1, 2, 3, 4, 5. I'm just so close. Like it's just so like, how come I can't get that? I can't get there. 1, 2, 3, 4, 5. I think we're getting new numbers. The high rolls are definitely lower. 1, 2, 3, 4, 5. Maybe I'm wrong. I don't know. Oh. 1, 2, 3, 4, 5. Actually, both of these bounds are. This could just be the minimum of these two. Right, because this could just be UB3 now. And this could be so if I do less than or equal to UB1, that would be less than or equal to X means it's less than X plus 1, right? Which means we can take the min of UB1 plus 1 and UB2, make that UB4. Okay. No kidding. Wow. How about that? How about that? So many variables, though, you know, saving a little bit of stuff, but I don't know. I could just update this variable UB2 to UB3 and then UB2 again to UB4. Maybe that's what I need to do. We have too many variables here in the loop. Okay, it seems to have slowed things down a little bit. Let me try to optimize this a little bit further. Let me try. 1, 2, 3, 4, 5. Yeah, it's okay. So what I can do is take UB2 and not make it a constant, right? And then update UB2 to no, actually I think these do need to be, let's do UB2 and UB3. UV3 is going to be n minus I, and let's do UV2, and then UV3 is going to be UV1, which was n minus I think, plus 1. And the other one is, that was UV1. Yeah, okay, that's confusing. And then UV2 is this one, self. M, n minus I plus 1. Well, the min of these, this is definitely going to be smaller than this. So I can modify this. And then since this is just UV2, so this is, yeah, so I think these can all be updated this way. This could be itself, and then min of m and n itself gives me just m and n minus I, right? And then this is then itself and n minus I, which could just be, which actually it already is. It already is the smaller of these two, right? This actually doesn't have to change. I think. Maybe I'm wrong. I think that's right. I think that's okay. No, not okay. Wrong. Let's go back. I got something confused there. Whew. Okay, let's try that one again. It's like, oh boy. All those upper bounds. Let's try submitting it. Okay, it's still right. So this is correct. UV1 plus 1 is actually up here. Oh, I see. Okay. This is the min of this one. And UV2 is n minus I. Oh, I see. Okay. All right. Okay. So UV3 and let's do 2 and 3. Okay, I see. So that gets kind of confusing. So these are actually not related to each other, only related by this value. But one of these could be a lot larger than the other. Well, that's confusing. I see the problem here. Let's see if this is still correct. I think so. All right. Yeah. Thinking if I remove more variables, if that's better or worse. Curious. I think it's generally better to remove variables. I don't know. I don't seem to be getting lower than, I don't seem to be getting to the 0% though, or the 100%, 0 milliseconds. I think I'm getting closer, but I would need to find more optimizations here, I think. Wondering if maybe I can front load this calculation too. So I don't need to recalculate this every time in the inner loop. So that would be another upper bound. So this is going to be I plus m bit shifted by 1 is greater than n, which is m bit shifted by 1 is greater than or equal to n minus I, which is then 2 times m n minus I, which is then m is greater than n minus I divided by 2. What if this is odd? Say m is 4 and this is like 9 or 10. So if this is 4 and this is 9, divided by 2, it becomes 4. 4 is greater than or equal to 4. It's kind of a mistake, huh? Probably just want to add 1 then. So 8 is not greater than or equal to 9. But if I bit shift down, truncate, this will be a 4 rather than a 5. So it should be rounded up, which means you could just add 1, I think. Would want the ceiling of that. Is that the same? No, the floor plus 1 is not the same thing as the ceiling. So 4.5 to 5. If you take the floor, you get 4, add 1, you get 5. The ceiling of 4.5 is 5. However, the floor of 5 is 5. The ceiling of floor of 5 plus 1 is 6. The ceiling of 5 is 5. Oh, excuse me. Yeah. So it should be the ceiling of n minus I divided by 2. But I can add 1 here, actually. That one works. Because now you'll get it's like yeah, now that'll actually give you that'll give you the correct answer. Anyway, so I could do n minus I plus 1 bit shifted 1. And then say m is greater than or equal to UB1. Pretty sure that works. Pretty sure that works, and that should give a little bit of relief. I'm back. Hey, welcome back. I was able to solve this. Well, I solved it before with my own solution, and then I looked at what's online, available online, and I used that solution because it was a good one. Slightly improved from what I had. Actually, significantly improved, a lot faster. And I've been trying to get this down to 0 milliseconds. I'm trying to improve the run speed here. There we go. Okay, well that's a little bit better. Like I'm trying to get it down to 0 milliseconds. It's at 3. It's faster than most of the solutions, but not all of them. I'm trying to figure out a way to make that happen. Okay, that was definitely an improvement, I think. 1, 2, 3. I think I'm gonna stop soon though, because I think I should go on to another question. 1, 2, 3, 4, 5. I don't think it improves it that much though. 1, 2, 3, 4, 5. These are like really minor improvements. But I don't think I'm getting to the 0 millisecond mark. I don't think I'm getting to the 100% mark. I'm like very close, but something's not quite gonna give. I mean, maybe this is what I need. I mean, I tried this before. I don't think this matters that much. I mean, maybe it does. Maybe it does. I don't know. 1, 2, 3, 4, 5. I don't think so. It's just clearing the array. Like it doesn't. Actually, I think it seems better if I do this first. But I don't know. I can't think of any other optimizations that might improve this. Maybe instead of using min, I can use an if statement. I think that sometimes improves things. But that's kind of bad. I don't really know. You know, it seems maybe. Doubt it. I think if statements are a little. Oh. Logical error. Or typo, or yeah, logical error. Sometimes maybe. Sometimes one is faster than the other. It's like hard to tell. I think an if statement, a branch is faster than a function call. That's kind of, but I think these get optimized out anyway. So I don't know. I don't know if that really matters that much. Kind of, like I said, it's kind of hard to tell. 1, 2, 3, 4, 5. I don't know. It's faster, man. I don't know. I don't know. It seems kind of random. Whatever. Anyway, I think I'll move on to the next thing. That's probably enough. This is pretty. I'm trying to do all kinds of micro optimizations here, but it's probably not worth the time. So anyway, that's something I've been thinking about lately. Is like I spend quite a lot of time just kind of dwelling on a question, trying very hard to like either solve something that's probably not possible or try to like optimize something that doesn't really need to be optimized. It's like it's just too much focus on the wrong things, I think. All right. So yeah, thank you for watching. Like the video if you like this kind of thing, and subscribe for more. And I'm gonna stop. I think I'm gonna take a break because I just spent a lot of time thinking here. I kind of just want to take a moment, take a break, and actually, wait. Before I go, hold on. I do want to just take a quick look at the other solutions. Let's see. Yeah. Very much similar ideas. Oh, this looks very clean. Oh, this one was right. Well, the other one. Hold on. It's about the same. I mean, I just broke these loops up, but yeah, it's triple for loop. That's fine. Beats 100%. Hold on. Helper. Maybe the top down is the way to go. Yeah. Top down apparently gives 100%. Maybe that's what I should have done. Else for input 1, which, oof. I don't know, I wonder. Also 100%. Oh, the same one. Yeah, I don't know. It's a little weird. I don't know what to say. I'm surprised this one is so fast. I'm surprised. I would assume the DP bottom up is faster, but I guess it's not. So anyway, a little disappointed on my end. It took me a while to code it in with my own solution, and then there's a slightly better way of doing it that you could bottom up. But the bottom up was not as fast, which is weird, not as fast as the recursion. Apparently the recursion is a little bit faster, which is not typical. But anyway, 0 milliseconds. What? Oh. M will not exceed 32. Yeah. Okay, that's a fair point. So that's maybe actually that might be the problem here. Is I need to optimize this with a constant M. Okay. Most of the DFS I think is a little bit faster too. It seems. Seems the DFS is a little bit faster. Oh, no. Okay. I didn't think about that. Okay, hold on. Let's go back to my. I should have thought about that, quite frankly. I don't know why. I'm like trying to optimize things that are not really. Oh no, this submission. Trying to optimize things that are not actually that important to optimize. I should have thought about that to optimize the memories amount. That actually matters a lot. I didn't even think about that. I kind of knew that too. That like this wasn't gonna be that much larger. M. This really should be 32, I think. Which is just 32. Bound is 32. It's just 32. It's just 32. I think that makes things a lot faster. I think so. Let me go back to my. Did not even think about that. I kind of knew that too. I was like, oh, there's like a logarithmic thing going on here because there's a logarithmic thing going on here because of this also should be the other way around. It should be bound and n, which means these things get reversed. I'm not sure if that matters. Let me keep it as it is for now. M. What is going on? How come? Wait. What is going on? Why am I running into issues here? Line 30. I think this doesn't matter. It's confusing. I think this also is just bound as well. And this maybe should be 33, actually, 31, 32, something like that. Let's do 33. I'm thinking I made some mistake here. Something's not quite right. Okay. Didn't think it all the way through, I guess. Let's do another one with larger values. Okay, I'm gonna go for it. This may or may not be correct. Oh, okay. 1, 2, 3, 4, 5. This is kind of interesting. No, not much better. 1, 2, 3, 4, 5. G. Oh, there we go. Hey, 100%. Okay. Got there. Took a while, but we got there. Wonder if this is, I could remove one there. I think I can. I'm gonna go for it. A little nervous to do that. Oh no! Oh, okay. I shouldn't have tried that one. 1, 2, 3, 4, 5. Yeah, I was like, wait, can I do this? No. Okay. But I got 0 milliseconds. All right. I shouldn't have tried I shouldn't have risked it. I don't know how I did that. It's doing so well too. It's funny. All right. That's enough. That's enough. Yeah. Okay. So use some optimizations that I found in other solutions to get to 0 milliseconds. I knew I could have, if I thought more about this, I could have gotten both of those. I think. One of them was, yeah, you don't have, you could look at the player like each player being just a different perspective and the same function being used for both players. That's one idea, and then the other idea is that you can reduce the. So that's actually why the DFS, the recursive solution, would be faster in some cases, is because the recursion tree is only logarithmic, and the DP that I did was like 3 times longer than it needed to be the memory and the actual amount of computing. So you actually were doing less computing with the recursive approach because of that. That was why. So I needed to lower the boundary on that. It's doing a lot of extra work, and again, it's cubic time. It's cubic time. It's cubic time. It's a cubic time algorithm. So the optimizations that are they're like compounded 3 times, or the lack of an optimization. So that was really important to reduce the bound, reduce how much extra work this is doing. So yeah, this second inner loop becomes a lot smaller. It's definitely makes a big impact on the amount of time it takes. Yep, there we go. So we're getting 100% consistently now because of that. Okay, yeah, that was a much bigger improvement. All right, let me stop there. So yeah, not bad. LeetCode's hard, man. I have to say. Got to find those little optimizations, I suppose. There's always like something more you can find. Also, so many stone games. Look at how many stone games there are. There's still so much more. Alrighty. Thank you for watching. I'll talk to you soon. Yeah, like the video if you like this. Subscribe for more. And yeah, I'm out of here. I'm gonna stop here, take a break, and then maybe come back and do another question. I think that'll be the plan. Okay, take care.